Hello, good evening, good afternoon. Name is Boris Jeremic, professor at UC Davis. This is our spring lecture series that where we cover topics in realistic modeling and simulation of earthquakes, soils, structures, and their interaction. Today with me are Dr. Han Yang.
Hello.
And Mr. Heshan Wang.
Hello.
And they will also be participating in this lecture today, but they will actually talk a little more in the next few weeks or so in some specialized lectures in topics that they're actually doing for research. Today, let me start sharing my screen. Share screen. Today's lecture is about seismic input. How do we input seismic motions into finite element models? Remember, our main motivation is really to improve seismic design, or in general modeling and simulation of infrastructure objects, which means soils and structures. We would like to be able to use high fidelity models or necessary level of fidelity models to get proper results, so that our design and our assessment of objects has a good value, and so that we can improve safety and improve economy. We are very keen on reducing so-called modeling uncertainty, because we want to be able to know with large certainty what are simplifications in our models doing to our results. If we simplify a very complicated structure to a single beam, we would like to know how our results from that simple beam different than results from a very complicated structure. And so you should be able, in order to do that, you should be able to go to that higher level of sophistication. And that's the whole purpose of the research we do. So we want to be able to go 1 or 2 levels of sophistication higher. And if we see that results don't change much, and again, it's up to the analyst, to engineer, to decide what does it mean much. 1%, maybe too low, maybe 10% might be okay. If results change 50%, then it might be not right to make such simplification, but you need to be able to go to higher level of sophistication. So with that, let's talk about seismic input. Imagine having a finite element model, structure and soil all together, and you're trying to input seismic motions. And so what people have done a long time ago was to take a bottom of just a structure and just apply some motions here by essentially pushing this support with displacements or accelerations. Maybe not bad, can be done much better. You can actually do that with putting soil underneath. So this is a model for soil and then a structure on top. And you can then take bottom of soil and shake the bottom of soil, and the wave is going to propagate through the soil, maybe inclined wave. In this case, actually, it's not right, or it's not possible to input an inclined wave. So you will have a wave propagating vertically and then shaking the structure. That's one way to do it. You can apply at the bottom, you can apply either displacements or accelerations. Another way to do it is to actually use relative accelerations, as I note here in the first item, which means that you analyze your structure or your soil structure system with accelerations that are relative to some moving frame of reference. And that might be okay too, but it suffers from a number of drawbacks. Some commercial programs use methods that are somewhat tricky. They would take a free field, or maybe even free field with some structure on top, and have a column of elements on the side here. And then they would propagate 1D way through this column of elements, and then they would connect this one column of elements with some springs and dashpots. And so this one column of elements is supposed to excite. It's a trick. It works in few cases. In most cases, it doesn't work. About 20 years ago, there was a method developed that was published about actually 17 years ago, so-called domain reduction method. The domain reduction method was developed by Jacobo Bielak from Carnegie Mellon. I think first papers actually appeared in '87, and then slowly they perfected the method, and eventually the paper appeared in 2003. Although I was lucky enough, Jacobo gave me a draft paper in 2001. It took 2 years to publish that paper. It's an ingenious method. It's really a revolutionary paper. and it took 2 years to publish because this method essentially makes all the other methods obsolete. And we'll go through details of this method in a second, but I just want to say that method essentially covers general 6-component input, so you can have all 3 translations and all 3 rotations, whichever way you want. I mean, rotations are obtained essentially by having variable translations at locations. You can have a nonlinear response inside the boundary, so-called boundary gamma, and outgoing waves are minimal. So the method actually very elegantly solves the radiation problem. The method consistently replaces seismic moments coming from the hypocenter and replaces them with a set of forces on a single layer of elements that surround soil structure system of interest. Very ingenious method. You'll see in a second. So let's assume that we have a model, a finite element model that looks like this down here. A very large model. There's even a seismic source that's inside the model. So this model might be 100 kilometers by 40 kilometers, in all 3 dimensions, 100 kilometers this way, 100 kilometers this way, and 40 kilometers this way. And so you have a seismic source, and far out somewhere you have a local feature. A local feature in this case, some type of building, can be a bridge, can be a tunnel inside, can be a dam. In this case, it's a building, it's actually a nuclear power plant. Let's say that we know the forces at the seismic source. This is usually known by seismologists, by geophysics people. There are different models how to predict what are the actual forces acting in the fault zone, and let's say that loading, that fault, is far away from our local feature that is now defined as a building and surrounding soil that is now within a boundary gamma. So this boundary gamma can be, doesn't have to be too large. The main point will be that this boundary gamma has to encompass all the elastic plastic soil. So if you think that your elastoplasticity is happening within few meters of your object, boundary gamma can be that small. Of course, it's a little better to make it a little bigger because you resolve some issues with some radiation damping. We'll talk about it in a second. But it doesn't have to be very large. It doesn't have to be 3-4 times the size of the object. It can be one size of the object at most. So this is our big model. We're trying to resolve an issue of how to transfer forces from the seismic source to the local feature. Let's assume now that we remove a local feature. We create a so-called free field model. And the model is defined here. What we have are forces on the inside, displacements on the inside, UI. This means U displacements, I inside. We have displacements on the boundary, and we have displacements on the outside. The E means external. 0 here means that we have those displacements in the free field model. Previous model had realistic inside displacements, realistic boundary displacements, and realistic external displacements. There's a boundary gamma, domain volume inside is called omega, volume outside is called omega plus. Going back, this now becomes omega 0 because we removed the local feature, the building, the bridge, the dam, the nuclear power plant. The outside still remains the same. There's no change in outside. It's still omega plus. So the only difference here is that these now displacements become displacement 0. So this is a so-called simplified large-scale domain. The domain is still huge. It's still 100 by 100 by 40 kilometers. So we haven't really done much to reduce the size of the domain, except that we removed the actual feature on top. Let's put some equations of motions for a complete system with the local feature. Mass matrix times accelerations, the Lambert's principle, inertia forces, plus stiffness times displacements equals to these forces. The only forces we have in this case are these excitation forces at the earthquake source. So this is our system. Again, we don't have any viscous damping in this system. We'll see later. We can add viscous damping later, but at this point, this is just a system of equations we're looking at. So I'm going to write, let's go back one slide. This same system is going to actually have now mass matrix and stiffness matrix and accelerations and displacements. There will be three components of those. There will be displacements inside, displacements on the boundary, displacements on the outside. Same thing with accelerations. So we're going to split up this into these three sets. We're going to have displacements on the inside, displacements on the boundary here, and displacements on the outside. Same thing happens to accelerations. Likewise, components of mass and stiffness, components of mass, for example, that belong to elements that only have nodes that are inside, they're going to be called MII. Components of finite elements, of mass matrices of elements that have all the nodes on the boundary are here, and those that are outside are going to be essentially here. Same thing for those stiffnesses. There are off-diagonal terms, elements that have nodes both inside and on the boundary, and elements that have nodes both on the boundary and on the outside. Okay, let's go forward. So now we're actually going to split the system into two subsystems. Now it's a simple thing, but there are two main things we need to enforce with it. So this system of equations, dynamic system equations, we say we're going to split up in two sub-equations, and they look like this. This will be for I's and B's. This is for internal and for these that are on the boundary. And these are for B's and E's. These are on boundary and external. What do we need to enforce in case of splitting the system into two subsystems? First thing we need to enforce is the compatibility of displacements. And going back one slide, we do that because right now we have boundary displacements here, and we have the exactly same boundary displacements here. So we do enforce compatibility of displacements. The other thing, when you split up domain into two subdomains, there will be some reaction and reaction between two subdomains, and those are those PB forces. The equilibrium action-reaction force PB. So going back to the system, so what we had as a one system, let's go back this, one system of equations, we now have two systems of equations where we know that we have compatibility of displacements, UB and UB is the same, UB double dot and UB double dot is the same, and we have equilibrium at the boundary where we split them in two parts. We have these action-reaction forces PB. So we end up with two systems of equations. Let's now look at the actual simplified interior domain that's inside that has those UIs, UBs, and so on, without local feature. And then we look at the exterior domain that's outside. We can actually write that previous equation for the domain outside by using zeros here, which means essentially displacements and accelerations on the boundary and on the outside for a free field domain without local feature. So we think that these on the outside, we can write them down as a free field, and they're far away from the boundary so that they're not going to be affected that much. And we'll see that actually there will be a slight change in variables coming soon. So let's use the previous equation, second part, and let's solve for PE. Let's solve for PE by essentially multiplying these two matrices with this vector, this matrix with this vector, and let's solve for PE. What comes out is an equation that looks like this. PE equals these mass terms times accelerations plus stiffness terms times appropriate displacements. So that's our solution for PE for a simplified outside domain. Okay. Now what we do is we do a so-called change of variables. The total displacements on the outside, those are displacements on the outside here, are going to be made up of two sets of displacements. One is so-called free field displacements, U0E. So these are displacements when there's no local feature, and a so-called residual field, WE. Those are additional displacements that are present because now we actually have a structure on top, and structure oscillates a little bit. There is a change in the field outside because the structure oscillates a little bit and maybe sends a little bit of additional waves to the outside. So the displacements on the outside is now made up of displacements from the free field when there's no structure and an additional field, so-called residual field, that is present because the structure oscillates and sends a little bit of additional waves outside. Again, this is not superposition for the whole system. This is just superposition for the outside. In fact, it's a change of variables for the outside. Okay, so what we do, we go to the original system of equations, and we just replace that last variable that was UE, the external accelerations and displacements, with this new one, which is going to be free field plus additional wave field because of the presence of local feature. Good. And here we still just have the PE and everything else. Now what we can do, we can take, let's go back one slide. We can take these free field displacements, the ones that we can know somehow, we'll talk about it in a second, and multiply them with appropriate components of matrix. And because they are known, they're free field displacements, they are known, therefore, we're going to multiply them and move them to the other side of the equality sign. And so that's happening here. So here on the right-hand side, we have the original PE plus these additional terms because of free field motions. And what we have left on the left side is the original displacements on the inside, displacements on the boundary, and additional wave fields on the outside. Still very large model. We just did this change of variables and we solved for PE for the free field model. So in the previous equation, we can actually substitute solution for PE from a couple of slides ago. And we end up with a system that looks like this. Again, inside displacements, boundary displacements, additional field on the outside, and the forcing function looks like this. It's made up of mass terms and stiffness terms of for the free field motions on the outside and on the boundary. What that is, that becomes a so-called effective force, DRM effective force, and it's written here as in terms of what's actually applied on the inside, on the boundary, and on the outside. Please note one thing. These are accelerations in the free field. These are displacements in the free field, and they're multiplied with appropriate mass and stiffness terms that have these indices BE, BE, and EB and EB. What does it mean? What do those indices mean? Well, if you look at the system just like what we had before, here's our big system. Which elements, which mass matrices and which stiffness matrices of which elements will have nodes that are both E and B at the same time? Well, so remember, B are nodes that belong to this boundary gamma. I are all the nodes inside. E are all the nodes on the outside. There's a single layer of elements that has nodes that are both B and E. And that layer is given here. So here's one example element. Let's say a quad element. Again, this is all for full 3D, but this quad is just to illustrate. So here's one element right here. This element has nodes B, and nodes E, nodes E. So this element is actually going to have matrix, going one slide back, it's going to have matrix MBE, MEB, and KBE, and KBE, and KEB. Just one layer of elements. All the other ones are dropping out. They don't exist anymore. So we multiply those off-diagonal terms with free field displacements at nodes E, and free field accelerations and displacements at nodes B and nodes B. So what we have done really is we have replaced this force PE with the effective force. Whatever displacements in this whole system were produced by the source, by the seismic source, are now replaced by this effective force. Of course, local, this is all happening here locally. So this is actually displacements and accelerations are going to happen here locally. We don't really worry much about what happens at the source. not at least for civil engineers. We worry about this part here. This effective force is applied only to a single layer of elements that is outside of this boundary gamma. If you go back a few slides and look at the big equation, you see that now we also have a change of variables. We are not solving for UE, we are now solving for WE. WE is just, going back to the slide I was just at, we're just solving for the outgoing waves from dynamics of the actual object, local object. We don't really worry much about displacements on the outside except for free field displacements. We really worry about this part here. So on the outside, we only solve for WE. Fair enough. Because we did this change of variables on the outside, we have not made any assumptions of what material can we have inside. Outside has to be linear elastic, but inside can be elastic plastic. There's no reason why it should not be elastic plastic inside. And because we can have any free field we want, we can solve that. We'll talk about it next time. Any free, we can even measure it. Any wave field can be input. And I'll show you a few examples. Now, all these nice features, all these nice 5 points, but we still have a huge model. But in reality, we don't really care about this outside. I mean, it's nice, and we talk to our geophysics and geology colleagues, but we're really interested in this initial part. So what we can do, we can neglect all the solutions on the outside, we can neglect that, and we can cut our model to be approximately this large. This one layer of elements is required, and you have to have at least one more layer, but let's say you have 2-3 layers on the outside. That's what we usually do, and I'll show examples with that. And that's all you need. So instead of having a model that's going to be 100 kilometers by 100 kilometers by 40 kilometers, you can have a model that's going to be, I don't know, 200 meters by 200 meters by maybe 50 meters. Depends on the object, of course, but it's a huge reduction. So I'll just illustrate this with few examples that you've seen before, but here I'm going to actually make them big. So here's that one example where we illustrated the full 3D wave field. So here's, let's go back just one. So look at this layer of elements, and this layer of elements, and this layer of elements. That's our DRM layer. These nodes, this node here is E node, this node here is a B node. All the other nodes inside are I nodes. So here's an E node, B node, E node, B node. This layer of elements is receiving those forces. And let's see what happens when that layer of elements receives those forces. This layer of elements deforms a lot, inputs wave inside the free field that we generated one way. We had a larger model to do that. There's also analytic way. Heshen is going to talk about that next time a little bit. But there's a very realistic wave coming in, and because it's a free field, 0 comes out theoretically. So in fact, a long time ago we had some, one thing that you learn about finite elements, you should always put you should put enough boundary conditions to prevent rigid body modes. We played some 15, 16, 17 years ago, and we actually removed all the boundaries. And if you have a proper solver, you can have a model with no boundary conditions at all. You have to do pivoting. You have to be very careful about how you solve system equations. And the whole system was essentially just floating in the air. Nothing was coming out with the air. So please observe how these waves are input inside through this one layer of elements, and nothing comes out. So this is a full realistic 6-component wave field. In fact, in this case, it's really a 3-component because it has components in this plane and some rotational components. There's no lob wave, there are no waves out of this plane. But it's in general, you can input any wave field. Any wave field, simplified wave field, 1-component wave field is also possible. It's no problem at all. It's just here it is. Again, this layer of elements, this and this and this gets loaded with forces, and those forces are consistent replacement of the forces from the source that produce that free field, and therefore your free field, in this case 1-component free field, is exactly input in the system. Very, very powerful method. And eventually, of course, you want to put the structure on top, and so next example actually does that. It's a little more complicated example, but just focus on this part here. This is energy dissipation example. Dr. Young is going to talk about that later, but just focus on this on this power plant, on this big building, heavy building. Here's the DRM layer, the corner, and we got free field motions from a large regional scale modeling from some colleagues from Livermore. And you see how the whole system oscillates. Now, because there's a very heavy structure, there's tiny bit of oscillations on the outside, but we can damp those out without much problem. So very realistic motion. This is a fling motion, so the whole neighborhood goes down and starts to wobble and so on. Very realistic motions input inside the system, and the system just behaves as it should. So with that, I'll stop, and we'll continue next time talking about how to develop these motions. There are a few ways to do this. Hesh is going to talk about analytic way to do this, and then we're going to also talk about energy dissipation. That's going to be linked to plasticity, and Dr. Han is going to talk about it later on. So thanks for your attention. Let me stop sharing, and I will stop recording here. Thank you. I will see you next time.